Well, hello, good people. I hope you're having a wonderful day today. We are talking today about mechanical energy and the work kinetic energy theorem. We're going to start today with a definition of mechanical energy. Now, you remember that the last time that we talked, we gave a definition for energy that was somewhat weak. We said that work was the transfer of energy, or work was transferred energy, and then we said that energy is the ability to do work, which means if you have energy, you have the ability to transfer it, which is not exactly a wonderful definition for energy and is kind of a lame definition for energy. Well, today we're going to be talking about the definition of energy really by looking at some different examples of some different types of energy. So, we'll talk about a few different types of energy that you already know about. For example, you already know about chemical potential energy, which is energy stored in chemical bonds. That's why you eat breakfast in the morning, is because there's energy stored in those little molecules, and when those molecules break down, they release energy that allows you to do things. Oh, you also know about other types of energy, like electric energy or electrical energy. That is totally a type of energy that powers your house. Well, today we're going to talk about mechanical energy, which is a broader category for a few types of energy that fit into that category. Here is our definition for, I organized this all beforehand. Okay. Ta-da! Wow, that was magical and so much faster than writing. Here's our definition for mechanical energy. We say that mechanical energy is energy due to the relative positions of the objects in a system or due to motion. It's energy due to the relative positions of the objects in a system or energy due to motion. Now, as you're looking at this, you can probably see that there are actually two types of energies that go under the category of mechanical energy. One type of energy, oh, hello, there's the bell. One type of energy that fits in the category of mechanical energy is this energy due to the relative positions. Hello? Wait. Due to the relative positions. Show. Oh gosh, wow, this is just really not going well for me. This is what I take for trying to plan ahead. Or what I get for trying to plan ahead. Never do that. That's bad. Okay, do it again. Show. Okay. Well, anyway, okay, I'll move on. I'm not going to keep doing this. Mechanical energy, there's the first type of energy, which is energy that is due to the relative positions of the objects in a system. That is what we call potential energy. And then there's another type of energy, which is energy due to motion. And that is what we call kinetic energy. Let me show these here. Okay, so we have two types of energies. There's potential energy, which is the energy that is due to the relative positions of the objects in a system. And then we have kinetic energy, which is energy that is due to motion. Both of these two types of energies make up what we call mechanical energy. They both fit into the mechanical energy category. We'll start today by talking about potential energy, and then after we talk about potential energy, then we'll talk kinetic energy. Let's start with a discussion of potential energy here. Potential energy is energy due to the relative positions of the objects in a system. Potential energy is what we call a stored energy. It's energy that is stored, and it's energy that has the potential to become kinetic energy, which is why we call it potential energy, is because it has the potential to become kinetic energy. An example of this would be like a stretched rubber band. If I take a rubber band and I stretch it, well, then I have changed the position, the relative positions of the parts of the rubber band, so that now they used to be close together. Now the parts of the rubber band are further away from each other. And I have just created some stored energy that has the potential to become kinetic energy if I release it. So potential energy is energy due to position. It's energy that's stored that has the potential to become kinetic energy. Another example very close to this, elastic potential energy, which is what we see with rubber bands. Something similar would be spring potential energy. A spring stores potential energy. When you pull down on a spring, then it has the potential, because now you've changed the position of the objects within the spring system. When you pull down on a spring, you have changed the position of things so that now it has the potential to go flying. So that if you let go of that spring, now it has some kinetic energy, energy due to motion. Another example would be something like electric potential energy. If I had a little positive charge and a little positive charge and I force them to be right next to each other in a position where they're very uncomfortable and I say, sit next to each other, guys, then they would say, no, and they would complain. But if I force them to be right next to each other, then that positive charge and that positive charge, because of their relative positions relative to each other, since they're close together, they have a lot of potential to go flying apart if I let them go. Same thing if I took a positive charge and a negative charge and I pulled them apart, then they would have, because of their positions, potential to go flying back together if I let them go again. So there are lots of different types of potential energy. We are going to focus in on one type of potential energy today, and that one type of potential energy that we are going to focus in on today is what we call gravitational potential energy. Whoa, my pen is doing weird things. Okay, sorry. Gravitational potential energy. Now, if you had to choose one letter to represent potential energy, you would, of course, most logically choose the letter U. Now, most students will say at first, if I say, what letter would you logically choose? They will choose the letter P for potential, but we do not use the letter P for potential because we already know that from yesterday that P means power. And so that is not a good choice. So instead we use U. Some textbooks will use PE for potential energy or GPE for gravitational potential energy. We will do no such thing in this class. We will never use PE and we will never use GPE. And here's the reason why. Is because P, as you know, means power. E means electric field strength, or it can also mean total energy. And capital letter G means the gravitational constant. If you say GPE, it does look as though you are appearing to say the gravitational constant times power times the electric field strength, which is not at all what you mean. When we use multiple letters, it's impossible to tell, are those multiple letters just variables being multiplied by each other, or are those multiple letters representing one thing? So in my class, we will never use multiple letters to represent a variable. We'll use one letter, and then we'll use subscripts to be more specific about what we're looking at. So we call potential energy U. The reason why we use U actually is you'll see a little bit later when we get into things like electric potential and electric potential energy. But we use U. It's a very nice letter. It's what the AP people use for potential energy, is they always use the letter U. And so that's what we use too, to reflect what they do. And that has been kind of the standard, has been to use U for potential energy. So we'll always use U for potential energy in keeping with the AP people and tradition. We will never, ever, 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 ever use multiple letters like this. Okay. If I wanted to talk about gravitational potential energy, then I would call this U lowercase g. Gravitational potential energy is this energy that results because of the gravitational attraction between two objects. So if you had like two things that are gravitationally attracted towards each other and then you pull them apart, the same way that if you pulled apart like a positive charge and a negative charge, if you pull them apart, then all of a sudden you have given them the potential to go flying back together again. And so that's what gravitational potential energy is. Now, in class, I say, hey, right now, if I'm standing on the ground, here is, I will draw. Here is me on the ground. If I am standing on the ground, or if you are standing on the ground, then on the ground, we don't have a lot of gravitational potential energy because we are very close to the earth. And so there's not a lot. Wow, I look amazing. That's me. Okay, so standing on the surface of the earth, I don't have a lot of gravitational potential energy because even though the earth and I are gravitationally pulled towards each other, right now we're very, very close to each other. And so there's not a big potential of stored energy that could turn into kinetic energy. If I'm standing on the ground, I don't have a lot of potential to fall. I don't have a lot of potential to have a lot of kinetic energy. So if I'm standing on the ground, then my potential energy is very low. But if I were to stand on something, like suppose I were to stand on a table. That's a table. This is me on the table. And wow, this looks so fun to stand on a table. Yes, you should try it at home with the permission of your parents. If they allow table standing, that is great. Okay, if I stand up here, now all of a sudden I have created some separation between me and the earth. And so I have just, I'm going to color in my table. And so I have just increased my gravitational potential energy because now I am a little bit further from the earth. So I now, standing on this table, have some potential to have some kinetic energy. If I step off of this table, then the earth and I could go rushing towards each other. Notice the way that I talk about this with my language. I would say that by stepping up on a table, I have increased the gravitational potential energy of the Earth, Miss Wilson system. We together, the Earth and Miss Wilson, now have more gravitational potential energy because we're now further apart, and so we have the potential to go flying towards each other. Now, granted, when I step off the table, who's going to accelerate more, me or the Earth? You say, Miss Wilson, yes, you are going to accelerate way more than the Earth because the Earth has so much mass, and I say, yes, all this is true. But we together have this potential energy to go flying towards each other. So when we talk about gravitational potential energy, we got to talk in terms of systems, because if there was only me there and no Earth, then I would have no potential energy. So when I stand on top of the table, I have some gravitational potential energy that I did not have before. In fact, in going from here on the ground to here on the table, I have added some gravitational potential energy. If I wanted to ask the question, how much gravitational potential energy did I transfer to the Miss Wilson Earth system when I went from here to being on the table, I would be asking, how much work did I do when I went from being on the ground to being on the table? Let's see if we can calculate the amount of gravitational potential energy that I added to the system by calculating how much work I did when I jumped up on the table. We know that the work, the energy that I added, is equal to the force that I applied times the distance that I went. Now I tell students, okay, what is the force that I applied? Well, we know that the amount of force that it takes to lift something is as much as that thing weighs. So the amount of force that I had applied to myself to get myself up onto the table, I had to apply a force of mg. And the distance that I went, well, that was basically the height of the table is how far I went, because my feet used to be on the ground and now my feet are on the table. So this little distance, the height of the table, that is my displacement. Now we could call it a delta x, we could call it a delta y, but I'm going to call it a delta h because it's a change in height. The next question that I ask my students is I ask, was my work positive or negative? And this one gets a little tricky for them, but there are two ways to think about it. First, I went up, so that's the direction of my displacement, and I had to push myself up in order to go up. So the direction of my force was up, and the direction of my displacement is up. And so if they're both in the same direction, then we call this positive work. But the easier way to think about it is I just added potential energy to the Miss Wilson Earth system. And if I just added energy to the system, then we call that positive work. This actually ends up becoming a generic formula for the amount of gravitational potential energy that is added to a system when you do work on that system to change the height. This is a new formula that is most certainly, most definitely worthy of your bag of tricks. We say that your change in gravitational potential energy is equal to your mass times g times your delta h. And now we're going to do a short practice problem using this equation. Go ahead and turn in your textbook to page 172. Okay, here we are on page 172. We're going to take a look at number 3b. If you read on page 172, you're going to be looking at the purple box there. It says, a 40-kilogram child is in a swing that is attached to ropes that are 2 meters long. Find the gravitational potential energy associated with the child relative to the child's lowest position under the following conditions. When the ropes are horizontal is part A, part B is when the ropes make a 30-degree angle with the vertical, and part C is at the bottom of the circular arc. Okay, The reason why we're going to walk through this one together is this one is just, the geometry here can get a little bit complicated. So I wanted to walk through it with you so that you can see. Okay, this guy right here is named Josh. And you can tell that his name is Josh based on the spikiness of his hair. Now, suppose that Josh was sitting on a swing, and Josh was sitting at the bottom of the swing, and then Josh was swinging on that swing. Question B asks, how much gravitational potential energy does he have when this angle here, theta, is when he's no longer heading straight down, but when he's at this angle here, and this angle theta is equal to 30.0 degrees. That's the question. This problem gives us some other information. It says that the mass of Josh is 40.0 kilograms. It also says that the ropes here are 2.00 meters long. I'm going to label that and I'm going to call it L. L is the length of the rope. So the rope for the swing is 2.00 meters. You can label this on your diagram here, or if you want to label it off to the side, then you can label it off to the side, and we'll say that the length of the ropes is 2.00 meters. The question is, what is the gravitational potential energy associated with the child, which is Josh, relative to when Josh is at the lowest point of the swing? So we're looking for a delta UG. What this problem is saying is it's saying, hey, consider that Josh, when he's at the low point, we're going to call that low point like point potential energy is equal to 0. Is the potential energy really 0 there? No, but we're going to call this our origin point. You know how with other problems we can establish where our origin is and then we can say we went this far away from the origin? Well, we can do similar things with energy. We're going to say that this point here where Josh is down at the bottom is going to be our 0 point, and we're looking for the change in potential energy from when Josh is at that 0 point to then when Josh is here. This is, I'll call this my delta UG final. So what I'm looking for is I'm looking for a change in potential energy here. Now you say, okay, Miss Wilson, no problem. I have a spiffy equation that I think will do just the job. I know that delta UG is equal to mg delta H, and that is absolutely true. If we were to plug in numbers, though, we'd get into a bit of a situation here real quick because M, we have it. G, we know it deep down in our hearts. But delta H is not the length of the swing. Take a look at our picture. Delta H is Josh's vertical displacement. It is this distance here, from here to here. This is Josh's distance. It's a delta H. So we have to find delta H. Now, in order to find delta H, I'm going to have to do a little bit of geometry work here. So here's what I'm going to do. I'm going to say, okay, looking at this situation, I know, first of all, that the length of the swing is L. And I also know that the length of the swing when it's at an angle is still L. So this distance here from like here to, wow, this is just a really poorly drawn. Let me try again. Okay, this distance here from here, the top of the swing, down to here, the bottom of the swing, that is still L even when it's at an angle. So that's one thing that I'm going to identify. And then the next thing that I'm going to do is I'm actually going to add in an additional variable here. And you'll see why in a second. I'm going to add in a distance D. And D is going to be the distance from, wait, let me try that again. Sorry, this diagram gets really messy. Okay, it's going to be the distance from the top of the swing here down to where Josh's new height is here. So it's going to be, I keep drawing the same line and it's looking very yucky, but you're getting the idea here. It's the distance from the top of the swing to Josh's new height when the swing is at an angle. So it's from here down to here. That is the distance D. The reason why I'm going to use this as a distance D is because I'm looking at this situation and I say, okay, if I'm looking for delta H, here's what I could do. I could say that H, or my delta H, is going to equal the total length of the swing, which is how far down he would be if he was at the bottom, minus d. Can you see, looking at this diagram, how that's true? That delta H, sorry, I'm going to write it a little bit smaller so that I have more space to work. That delta H, oh no, not the working sign of death. The delta H is equal to L minus D. Can you see why that would be true here, looking at your geometry? Then, here's what I'm thinking next. I know L. If I could just find D, then I would have an equation for delta H in terms of things that I know. So I'm going to look for D. When I'm looking for D here, I know this hypotenuse here. I know this angle theta, and would you look at that? This looks like a little triangle here where I'm looking for D. To find D, I can use some of my trig friends, and the trig friend that I'm going to use is cosine of theta. Looking at this problem, I say cosine of theta is going to equal D over L. Rearrange and solve for D, and I get that D is equal to L times the cosine of theta. So I can plug this in for D here, and I get that delta H is equal to L minus D, and D is L cosine of theta. And that is my delta H. Now I can plug this delta H into this equation over here. So I get delta UG is equal to M times G times L minus L times the cosine of theta. And now I have a nice algebraic expression for delta UG in terms of variables that I have. For the mass of Josh, I am going to plug in 40.0 kilograms. For G, I'm going to plug in 9.81 meters per second squared. Then for L, I'm going to plug in 2.00 meters minus 2.00 meters times the cosine of, oh no, 30.0 degrees. And I need another parenthesis there. Don't forget your other parenthesis. Okay, plug that into your calculator, and you would get something like 105 joules of energy. Okay, and there's the problem. Notice that the greater your height is, the more potential energy you have. And isn't that true? Like, the greater your height, the more potential that you have to get falling faster and faster and faster and faster. So that makes sense to us. Also, the more mass that you have, the more kinetic energy that you could possibly have. And we'll see why that's true in about 2 seconds. Let's talk a little bit about kinetic energy. Kinetic energy is energy due to motion. And I'm going to move this guy over here. Kinetic energy is energy due to motion. Energy due to motion. Now, kinetic energy is honestly pretty intuitive. If I asked you which would have more kinetic energy, a Toyota Camry going fast or a Toyota Camry going slow, you would probably say a Toyota Camry going fast. If I asked you which would have more kinetic energy, a Toyota Camry going fast or a semi-truck going fast, you would probably say it feels like intuitively that a semi-truck would have more kinetic energy, and that's absolutely true. So we say that kinetic energy depends on these 2 factors. It depends on your mass and your speed. Kinetic energy is equal to 1/2 mv squared. And that is our formula for kinetic energy. Yes, please do most definitely add it to your bag of tricks. Kinetic energy is equal to 1/2 mv squared. Now, I like to ask students, hey, what would happen to your kinetic energy if your mass doubles? What would happen to your kinetic energy if your mass is cut in half? What would happen to your kinetic energy if your speed doubles? And what would happen to your kinetic energy if your speed is cut in half? And let's take a look. If I double my mass, I would double my kinetic energy. And if I half my mass, I would half my kinetic energy. If I double my speed, well, my speed is squared. So doubling my speed would quadruple my kinetic energy. And if I cut my speed in half, well, that's squared too. So cutting my speed in half would quarter my kinetic energy. That's how this little square works in this equation. So I asked students, which one matters more for your kinetic energy, your mass and your speed? And students will most often correctly say, Ms. Wilson, your speed matters more for your kinetic energy. One other thing that I like to point out about kinetic energy is that kinetic energy is energy, and energy is a scalar, not a vector. So you'll notice that this velocity here is not a velocity at all. It's actually a speed. It has no vector hat, and your kinetic energy also has no vector hat. Hey, you might have seen it here. But if you had to choose one letter to represent kinetic energy, you would use, of course, the capital letter K. Again, we will not use KE. We will always just use one single letter to represent our variables, and that is the capital letter K. Now, we can talk a lot more about about kinetic energy, but before we do, there is one equation that we are going to derive here today. You can see how over when we talked gravitational potential energy over here, we talked about how work was related to a change in energy, and you can see that that's true. Well, there's also a relationship between work and your change in kinetic energy. And let's take a look at that little derivation to get to that equation here. First, you are going to need to know that V final squared equals V initial squared plus 2A delta X. We are going to start by rearranging this little equation to solve for the acceleration, and let's rearrange it to solve for delta X, and you'll see why here shortly. We'll do delta X is equal to V final squared minus V initial squared. Then we're going to have to divide that whole thing by 2A. Okay, now that we have this statement of truth, let's go back to work. We know that work is equal to force times displacement. Well, if you wanted to talk in terms of the net force, then we could call this F net, and then we would just have to call this net work because it's the work being done by all of the forces, or the total work being done. So we would have that this is the force times the displacement. Well, let's plug in here what we have for displacement. We would get F net times V final squared minus V initial squared all over 2A. Well, now take a look. We know that force is equal to mass times acceleration. So if we took mass times acceleration here, according to Newton's second law, we would get something like this. Notice, my accelerations would cancel out, and I would be left with something that looks like 1/2, if I pull out that 2, times m times V final squared minus V initial squared. Or if we expand this out, I'm running out of room here. If we expand this out, we get that the total amount of work is equal to 1/2 mv final squared minus 1/2 mv initial squared, which gives us this equation, that the total work done by the net force is equal to K final minus K initial, or, final statement here, that the total amount of work done by the net force is equal to your change in kinetic energy. This equation is what we call the work kinetic energy theorem, and it is a crazy, crazy valuable equation in physics. And as such, because of its worthiness, should most definitely be added to your bag of tricks. It is what we call, I'll write it down here, the work kinetic energy theorem. The work kinetic energy theorem is this equation, and it is truly an incredibly, incredibly useful equation in physics. Before we talk about how to use this equation mathematically, I want to talk about its significance conceptually. I'm going to pull up another page here so that we can take a look at an example of why this equation is so significant. Okay. Suppose that I have a cart and that I am pushing this cart across the table. Oh my GOSH, I can draw a cart. I really, truly, very most definitely can. Okay, suppose that I am pushing this cart across the table at a nice constant velocity. Suppose that it is going this way. This is the direction of my displacement. And we'll say that I am applying a force of Fa to this cart, but at the same time, there is a force, there is a force of, why can't I draw a straight line? I don't know. There is a force of friction, which is slowing the cart down. Let's take a look at what the work kinetic energy theorem would say in this case. The work kinetic energy theorem would say that the total work being done, or the work being done by the net force, is equal to your change in kinetic energy. Well, check it out. If I'm pushing the cart forward, am I doing some work? Yes, my work is the force that I'm putting in times the displacement. Is that work positive or negative? You say positive. It's a force that's going in the same direction as the displacement, so we would have positive work. So we would have positive work being done by the applied force. That positive work being done by the applied force, we'll come back to this force in a second, but that positive work being done by the applied force would be adding kinetic energy into the system. It would be trying to make the cart go faster and faster and faster. So it would be adding in kinetic energy, which we know that when you add in kinetic energy, or when you do positive work, that means you're adding in energy. So all of this makes sense to us. We say, yes, positive work would add in kinetic energy. Meanwhile, Fk is also doing work. We know Fk is doing work because it's a force that is being applied over a distance. Now, if I ask you if that work is positive or negative, you would say it's doing negative work because the force is anti-parallel. It's in the opposite direction of the displacement. So Fk would be doing negative work. And we'd say that makes sense because Fk would be taking kinetic energy out of the system. Fa is trying to make it speed up super, super fast. It's trying to make it go faster and faster and faster. But Fk is slowing it down. So Fa is putting energy in, Fk takes it out. Fa puts energy in, Fk takes it out. Fa puts energy in, Fk takes it out. It's kind of like if you had your bathtub on with the water running but the drain open. Fa is putting all that energy in, but then it just goes back out with the Fk. And so we would say that if these two are equal in size, like they are, and opposite in direction, then the net work in this case, you would have positive work from Fa and negative work from Fk. The net work in this case would be 0. And however much energy Fa puts in, Fk would take out all that energy again. So the total change in kinetic energy would be 0. So if the net work is 0, the change in kinetic energy is 0. Now check. The word change here is very, very important. The cart does have kinetic energy because it is moving, but the total change in kinetic energy is 0. In other words, we would say this guy is moving at a constant velocity. He's moving at a constant velocity because k equals 1/2 mv squared is not changing. There's no change in kinetic energy. No energy is being added that isn't being taken out again. And so the total change in kinetic energy is 0. So V is not changing. This cart is not speeding up. It is not slowing down. We have a constant velocity. Hey, do you see how this says something very, very similar to what Newton's second law would say about this situation? Here's what Newton's second law would say. Newton's second law says your acceleration is equal to your F net over your m. And Newton's second law would say, okay, we'll take a look at your F net. You have positive Fa minus Fk. And if those are the same size, then you have no net force. And so you have no acceleration. And isn't an acceleration just a change in speed? So you can see that both the work kinetic energy theorem here and Newton's second law Both say if the forces are the same and the total work is, if there's no net force and there's no net work, then we have a constant velocity. But they say it two different ways. The work kinetic energy theorem says we have a constant velocity by saying, hey, there's no change in the kinetic energy. The change in the kinetic energy is zero. Newton's second law says it by saying there is no acceleration. And if there's no acceleration, there's no change in speed. So they're both communicating the same thing here. Suppose, we'll do one more example here conceptually, and then we'll move along and talk a little bit mathematically. Suppose that we took FA and we made FA much longer than FK. If we made FA much longer than FK, then the work done by FA would be much bigger than the work done by FK. And so, as a result, the positive change in kinetic energy from FA would be bigger than the change in kinetic energy that FK is taking out. And so, as a result, you wouldn't have zeros here. You would have some change in kinetic energy, and you would have some work that's being done, some net work that's being done. Meanwhile, on the other side would say, well, if you were looking at Newton's second law, FA is bigger than FK, so you wouldn't have zero here. No, you would have something in the numerator here, which would mean that you have some acceleration. So this example would say, well, you have some change in kinetic energy, which means your speed changes. And this guy would say you have some acceleration, which means that your speed changes. So both of these are two different ways of telling the same story. The reason why the work kinetic energy theorem is very powerful is because it tells the same story as Newton's second law, but it tells that story with different variables. I want to show you a little bit how we can mathematically set up the work kinetic energy theorem in order to solve new types of problems. The work kinetic energy theorem says that the total amount of work done by the net force is equal to the changing kinetic energy of the system. Well, let's take a look at how you could use this mathematically. What you would do is you would start with the work kinetic energy theorem, and then you would say, okay, well, when we say work here, we mean the work done by the net force times the total displacement. Then you would say, well, this kinetic energy, it matters that it's a delta. That's going to be a K final minus a K initial. Then you could say, well, okay, the net work here, the net force times the displacement. Wow, my vector hat looked bad. Times the displacement, that's going to equal a 1/2 mv final squared minus a 1/2 mv initial squared. And from then, you could rearrange and solve for what you're looking for. If you want to add an extra algebraic step here, you could also do one of these moves where you do something like this. One second. Here on this side, you have these common factors of the 1/2 m. So you could take the 1/2 m out like this and have a v final squared minus a v initial squared. If you do that, quick thing to note, v final squared minus v initial squared, that is not the same thing at all. Sorry, move this out of the way. That is not the same thing at all as v final minus v initial squared. Oh no, I did this bad. These two equations are not saying the same thing at all, so be careful when you take out your variables. But what you can see here is this is a super, super nice expression that relates force and displacement and mass and velocities or speeds in ways that you actually haven't seen them related before. So the work kinetic energy theorem gives you a totally new way to kind of look at these kinds of problems. And that is all for today, folks. Today we talked about two types of energy. We talked about potential energy, and we talked about kinetic energy, both of which fall under this broader category that we call mechanical energy. When we talked about these two types of energy, we talked about potential energy and how there are different types, but we really honed in today on gravitational potential energy, and we came up with an equation for gravitational potential energy. Then we talked kinetic energy, which is energy due to motion. We had an equation for kinetic energy, and then we quickly moved on to talk about the work kinetic energy theorem, which relates the work that's done, which work just means transferred energy, by the way, to the amount of kinetic energy that is transferred to or from a system. Then we saw how this work kinetic energy theorem really works conceptually, and we looked at how you can use it mathematically to solve problems. And that is all for today, folks. I hope you do have a wonderful rest of your day, and I will see you all next time. Bye, good people.